Welcome to the Deep Dive, your shortcut to getting informed. Today we're looking into something fundamental, how we actually see the world around us. It's all about the physics of light.
Absolutely. Fascinating stuff, and often quite tricky. We're talking about mirrors, lenses, how light travels, and basically how our eyes get tricked or even helped by physics every single day.
Right, it's everywhere. So our mission today is to really unpack this science, make it into, well, a story you can follow. Let's start right at the beginning. What makes something visible? Why do we see things at all?
It sounds complex, but the basic idea is actually quite elegant. An object becomes visible when light, say from the sun or lamp, hits it.
Okay.
And then that light bounces off, it reflects, and that reflected light travels into your eye. Simple as that, really. No reflection, no sight.
And for a long time, everyone thought light just travels in perfectly straight lines. Like a beam, a ray of light. That's why shadows are sharp, isn't it? Light gets blocked, travels straight past the edges.
Yes, exactly. That ray model is super important for understanding mirrors and lenses, which we'll definitely get into. But here's the first twist, something the sources highlight right away. This straight line business, it's not always true.
Ah, okay. So when does it break down?
It breaks down when things get really, really tiny. We're talking microscopic obstacles. When light hits something that small, it doesn't just stop or go straight past. It actually bends. It sort of curls around the edges.
Curls around like water flowing around a rock.
Precisely. That effect is called diffraction. And to explain that, we have to think of light not as a straight ray, but as a wave.
Okay, light is a wave. But wait, did we also talk about using mirrors to...
That was the million-dollar question in physics for ages. It took quantum theory to sort of reconcile this. The modern understanding is that light is, well, both. It has this wave-particle duality. It's weird, I know.
Definitely sounds weird.
It's a huge topic on its own. But thankfully for today, for mirrors and glasses and how we see things generally, we can mostly stick with the simpler idea, the ray model. Light travels straight.
Okay, let's stick with the straight ray then. Phew. Let's move to section 1, reflection. The magic of mirrors. What are the absolute basics? The rules for light bouncing off any surface.
Good place to start. There are just two fundamental laws, and they apply whether the mirror is flat or curved. First, the angle the light comes in at the angle of incidence is exactly equal to the angle it bounces off at the angle of reflection.
Okay, angle in equals angle out. Makes sense.
And the second rule is about geometry. The incoming ray, the outgoing or reflected ray, and the normal, that's an imaginary line, perpendicular to the surface right where the light hits, they all lie flat on the same plane.
Got it. Like they're all drawn on the same flat sheet of paper.
Exactly. And these rules explain why your image in a normal flat bathroom mirror looks the way it does. It's upright, same size, seems to be behind the mirror.
And flipped left to right. Lateral inversion. Always makes you pause when reading text in a mirror.
Right. But the real fun, as you said, begins when the surface isn't flat anymore, when it's curved.
Let's talk spherical mirrors. The source mentions a great way to picture this. Just grab a shiny spoon.
Yes, a brilliant example. Look into the bowl side, the inside curve, then flip it over and look at the back, the outside curve. You see totally different reflections of your face.
The inside the bowl part, that's the one that seems to magnify sometimes, or flip things upside down if you're far away.
That's the concave mirror. It's reflecting surface curves inwards towards the center of the sphere it would be part of.
And the back of the spoon, the part that bulges out and makes things look smaller.
That's the convex mirror. It's reflecting surface curves outwards.
Okay, concave inwards, convex outwards. Before we talk about what they do, we need some terms, right? The geometry matters here.
It does. We need a few key reference points. Imagine the mirror is a slice of a big hollow glass ball. The center of the mirror surface itself, that's the pole, P.
Okay, P is the middle of the mirror bit.
Then the center of that original big sphere it was cut from, that's the center of curvature.
Right, C is the center of the whole ball.
The straight line going through both P and C is the principal axis. And maybe the most important point for understanding these mirrors is the principal focus.
F for focus. That's where the light rays meet up, or seem to.
Exactly. For mirrors that aren't too deeply curved, what we call small aperture mirrors, this focus point F sits perfectly halfway between the pole P and the center of curvature C.
Halfway.
Yep. And this gives us a really crucial, simple relationship. The distance from the pole P to the center C is called the radius of curvature. The distance from the pole P to the focus F is the focal length F. And the relationship is just R equals 2 times F, or F is R divided by 2.
R equals 2F. Simple, but sounds like it dictates everything.
It really does. It governs how these mirrors form images.
Let's see it in action with the concave mirror, the inward curving one. The source mentions activity 9.2, holding one up to the sun.
Ah, yes, the classic demonstration. You take a concave mirror, point it towards the sun. The sun's rays are coming in practically parallel because it's so far away, and the mirror gathers all that light.
And focuses it.
Precisely. It focuses it down onto a single, tiny, incredibly bright spot on a piece of paper. That spot is the image of the sun, formed right at the principal focus, F. And if you hold it there...
It gets hot. Hot enough to burn the paper.
That's right. It shows the power of convergence, all the parallel light energy concentrated at F.
And this converging property is why we use them in things like torches and headlights.
Absolutely. If you put a small bulb at the focus F of a concave mirror, the light rays go out, hit the mirror, and reflect back as a strong parallel beam, perfect for lighting the way.
Clever. Reverse the process.
Exactly. And the same principle, but on a massive scale, is used in solar furnaces. Huge concave reflectors concentrating sunlight to generate immense heat for industrial processes.
And what about closer up, like shaving mirrors or the ones dentists use? They magnify things.
Right. That's where the concave mirror shows its versatility. Unlike a flat mirror, where you put the object relative to the mirror drastically changes the image. For magnification, you need to place the object, your face, or a tooth very close to the mirror, specifically between the pole P and the focus F.
Closer than the focal point.
Yes. If you do that, the mirror produces an image that is virtual, meaning it appears behind the mirror, erect, the right way up, and significantly enlarged. Perfect for seeing detail.
So concave mirrors can converge light to burn things, create parallel beams, and magnify up close. Very useful.
Yeah, like highly versatile. Yes.
Now let's flip the spoon. The convex mirror, the one bulging outwards. Why are these the standard for car wing mirrors and rear view mirrors? They seem to do the opposite.
They do. Their primary characteristic is safety through a wider view. Because a convex mirror curves outwards, it always diverges the light rays that hit it. They spread out.
Spread out, so they don't form a real focal point like the concave mirror.
Correct. The reflected rays appear to diverge from a virtual focal point behind the mirror, and the result is that a convex mirror, always, no matter where the object is, forms an image that is virtual, erect, right way up, and diminished. Always smaller.
Ah, diminished. Smaller images. That's the key for the wide view, right?
Precisely. By shrinking the image of everything behind you, the mirror can fit more stuff into its frame. You sacrifice the size of individual cars, but you gain a much wider panoramic field of vision, essential for checking blind spots.
Makes sense. Safety over size. The source mentioned a cool example with the Taj Mahal.
Yes, a lovely illustration. Apparently, at the Agra Fort, there's a small convex mirror fitted on a wall, and standing at the right spot, you can see the entire reflection of the massive Taj Mahal within that tiny mirror. Shows just how much view you can pack in.
That's pretty amazing. Miniaturizing a monument with curved glass. Okay, so that covers reflection and mirrors. Now, what about when light doesn't bounce off but goes through something, like from air into water or glass?
Right, that's the next big phenomenon, refraction. This is all about light-changing medium. And it leads to some very common, slightly weird-looking effects we see all the time.
Like looking down into a swimming pool and the bottom looks closer than it really is.
Exactly. Or putting a coin in a bucket of water, it looks raised up. Try reaching for it where you see it, and you'll miss.
I've done that. And the classic one. A pencil or a straw in a glass of water. It looks bent or even broken right at the water surface.
Perfect examples. Also, if you place a thick slab of glass over some printed text, the letters seem to jump up, appear raised. All these visual distortions are down to refraction.
So what is refraction, fundamentally? If reflection is about bouncing, refraction is about
bending. Refraction is the change in the direction, the bending of the path of light when it travels from one transparent medium into another, hitting the boundary at an angle.
Why does it bend? What causes the change in direction?
It all comes down to speed. The speed of light isn't constant everywhere. It travels fastest in a vacuum, almost as fast in air, about 300 million meters per second, an incredible speed.
The famous C.
That's the one. But when light enters a different transparent material, like water or glass or diamond, it slows down. And it's this change in speed that causes the light ray to bend, to change its direction.
So the change in speed makes it bend. How much it bends must depend on the materials involved.
Absolutely. We measure this effect using the refractive index, usually given the symbol N. It's basically a number that tells you how much light slows down in that material compared to a vacuum. Higher refractive index means light travels slower in that medium.
Okay, refractive index N. So water has an N, glass has an N.
Yes, and the ratio of the speeds in the two media tells you the relative refractive index between them. But here's a really important point, something that often trips people up. We talk about materials being optically denser or optically rarer.
Denser means light travels slower, rarer means faster.
Correct. And this is key. Optical density is not the same thing as mass density. You know, how heavy something is for its size.
Wait, really? So something less heavy could actually be optically denser?
Yes. The source gives a perfect example, kerosene. Kerosene floats on water, right? So its mass density is lower than water.
Right.
But kerosene has a higher refractive index, about 1.44, than water, about 1.33. So optically speaking, kerosene is denser than water. It slows light down more, even though it's physically lighter.
Wow, okay. That's a crucial distinction. Optical density is just about light speed, not weight.
Exactly. Don't confuse the two.
So light slows down when it enters an optically denser medium. How does that relate to the direction it bends? Is there a rule?
There is, and it's related to that normal line, again, the perpendicular line to the surface. When light goes from a rarer medium, like air, where it's faster, into a denser medium, like water, where it's slower, it bends towards the normal. It gets pulled inward slightly.
Okay, rarer to denser bends towards the normal. What about going the other way? Denser to rarer, like light coming out of water back into air.
It does the opposite. As it speeds up, going into the rarer medium, it bends away from the normal. It swings outwards a bit.
Towards when slowing down, away when speeding up. That explains the bent pencil. Light from the submerged part travels from water, denser, to air, rarer, before reaching our eyes, so it bends away from the normal, making the pencil appear to be in a different position.
You've got it. That's the core of refraction.
All right, we've done reflection with mirrors, refraction with light bending through stuff. Now let's put refraction to work in section 3. Lenses. How we use this bending to focus light or correct vision.
Yes, lenses are all about harnessing refraction. Think of a simple magnifying glass, the kind a watchmaker might use. That's a lens.
And basically a lens is just a piece of transparent material, usually glass or plastic, with curved surfaces.
Typically bound by one or two spherical surfaces, yes. And just like mirrors, we have two main types based on their shape and how they affect light.
Let's start with the magnifying glass type. That one's thicker in the middle, thinner at the edges.
That's the convex lens. And just like the concave mirror, the convex lens is a converging lens. It takes parallel rays of light, like from the sun, and uses refraction to bend them inwards.
To meet at a focal point.
Exactly. Activity 9.11 in the source material mentions using a convex lens to focus sunlight onto paper and burn it. Same principle as the concave mirror, but achieved through refraction, bending through instead of reflection, bouncing off.
Converging lens, convex lens. Got it. What's the other type?
The other main type is thicker at the edges and thinner in the middle. This is the concave lens.
Okay, opposite shape, so it does the opposite thing to light.
It does. A concave lens is a diverging lens. When parallel rays of light pass through it, it refracts them outwards, makes them spread apart. They appear to originate from a virtual focal point on the same side the light came from.
So convex converges, concave diverges. How does this affect the images they form? Is it similar to the mirrors?
There are parallels, but also key differences. The convex lens, the converging one, is very versatile, much like the concave mirror. Depending on how far the object is, it can form real, inverted images, useful for projectors or cameras.
Or if you hold the object close enough.
If the object is closer than the focal length, the convex lens acts as a magnifier, producing a virtual, erect, and enlarged image. That's your standard magnifying glass effect.
Right, and the concave lens, the diverging one.
The concave lens is more predictable, like the convex mirror. It always, regardless of object position, forms an image that is virtual, erect, right way up, and diminished, always smaller.
Always virtual, erect, diminished for concave lenses. Okay.
Yeah.
This brings us nicely to eyeglasses. When an optician gives you a prescription, say plus 2.0 D or minus 1.5 D, what does that actually mean? What's the D?
The prescription. That D stands for diopter. It's the unit used to measure the power P of lens.
A power. Is that how much it bends light?
Essentially, yes. It's a measure of the degree of convergence or divergence. Mathematically, it's very simply defined. Power P is the reciprocal of the focal length, F, but crucially, the focal length must be measured in meters, so P equals 1F with F in meters.
T equals 1 over F. Simple. So if a lens has a power of plus 2.0 D,
then its focal length F is 1 divided by 2.0, which is 0.5 meters or 50 centimeters.
and the sign. Plus or minus.
Very important. A positive power, like plus 2.0D, indicates a converging lens, a convex lens. This is typically used to correct farsightedness, hypermetropia.
Okay, positive power includes convex and converging.
And a negative power, like minus 1.5D, indicates a diverging lens, a concave lens. Its focal length would be 1 minus 1.5, which is about minus 1.67 meters. Negative tower lenses are typically used to correct nearsightedness, myopia.
Concave, diverging, negative power. Makes sense.
No.
And this simple math must make the eye testing process much easier.
Absolutely. When the optician tries different lenses in front of your eye, often putting several thin lenses right next to each other, the total power of that combination is just the simple algebraic sum of the individual powers. P total equals P1 plus P2 plus P3 and so on.
So they can just add and subtract the diopter values to quickly find the exact correction you need.
That's precisely. It's a very convenient system. And this additive property isn't just for opticians, it's fundamental in designing complex optical systems like camera lenses or microscopes, which often use multiple lenses combined.
What a fantastic journey. We started with light itself, that weird wave particle thing. Then we saw how reflection, using the simple geometry of mirrors and that R2F rule, lets us see ourselves, drive safely, and even harness solar power.
Then we shifted to refraction, seeing how light bending due to changing speed explains everyday oddities, and introduced the crucial difference between optical and mass density.
And finally, lenses. Harnessing refraction with convex and concave shapes, converting or diverging light, all neatly quantified by the power and dioptries, P1F.
It ties together beautifully, doesn't it?
It really does. And that leads us perfectly to our final provocative thought for you, the listener.
Yeah.
We just heard that the power of lenses adds up, P equals P1 plus P2. The source mentions this is vital for complex instruments like cameras, not just for getting the right focus, but specifically for minimizing defects in the image.
Right, think about it. A single simple lens rarely forms a perfect image. One common issue is that glass bends different colors, different wavelengths of light, by slightly different amounts. This is called chromatic aberration.
So red light might focus at a slightly different point than blue light.
Exactly, leading to color fringes or blurriness, especially at the edges of the image.
Yeah.
So the question for you is, knowing that different lens shapes, convex, concave, and different types of glass refract color slightly differently, how do you think engineers combine multiple lenses, maybe a convex lens of one type of glass, with a concave lens of another, specifically to counteract this color fringing defect and produce a sharper, more accurate final image in your camera?
Something to ponder. How combining lenses corrects the flaws of individual ones. Go out and look at the world, the reflections, the refractions. It's all physics in action.